Hi, Jeff here, and welcome to the next tutorial in our Diva 4.0 tutorial series. Today we will be designing a PV system on the rooftop of our example office building pictured here. We'll be using the radiation map component in Diva to find the best location to locate our PV system. Then we'll also use the radiation map to optimize the rotation and placement of our PV panels. And we'll switch over to ArcSim to simulate the annual and monthly electricity output of our PV system. So we're using the example office Rhino file with the addition of a context building that is situated to the south of our example office building, and it's casting a shadow on the roof of our building. And we're able to visualize that shadow using the sun path component that you can refer back to in the previous tutorial. We're showing the kind of worst case scenario shadow being cast on 12 p.m. on December 21st. We'll use the radiation map to show the incident solar radiation falling on our rooftop to get a more quantitative evaluation of where to place a PV panel on that roof. So we are using the Diva assignments, material assignments for this tutorial in Rhino. So you have to have this file set up by setting a location and assigning the materials in the scene. You'll see that I already have some materials assigned for our context building and for the massing model, which contains our example office, as well as a couple of layers called PV and PV array, which I'll explain a little bit further on in the tutorial. This contains the geometry of the photovoltaic panels that we will be testing. I'll switch over to wireframe mode, and you'll also see that there is a surface modeled here on the top of our example office building that we'll use to reference for our analysis grid, but we won't be including this in the simulation. Great, now to begin, I will place the radiation map component onto the canvas, and that's located here. Now this radiation map component will simulate the total solar radiation falling on a surface, on any kind of input surface for a given time period. And that time period can be specified if we zoom in on the hidden inputs. If I press the plus, you'll see that there's a list of hidden inputs, and one of them is the start date, which is defaulting at 1/1, so January 1st, and there's an end date input, which is at December 31st. We can override these dates if we wanted to look at a specific time period, like, say, the summer, but for now we want to know the annual solar radiation incident on our surfaces, so we'll leave the defaults for now. We'll give this simulation a name. I'll call it PV, and I'll plug that in here. And now we need to tell our grasshopper component which surfaces to analyze for solar radiation, for the radiation map. So we'll use the grid input, the daylight grid input, which is what we used for our annual simulations in previous tutorials. For the geometry input, I'm going to reference that surface that we want to use for our grid here in the Rhino viewport. So I'll place a BREP container onto the canvas, and I'll set this surface here, which is on the grid layer, as our reference surface for our analysis grid. And for the spacing, I'll go ahead and leave the default spacing, which is 0.45 meters. I'll plug the grid output into the grid input. Now for the objects in our scene, as I mentioned, we'll be using the Rhino scene for our simulation, and we won't need to define any additional objects using grasshopper components, so I'll leave this OBJ input blank. And for the Rhino scene, I want to include the Rhino scene object, so I'll put a Boolean toggle onto the canvas, set that to true. So now we're including our context object as well as the example office. For the location, I'm going to go ahead and keep the default Boston Logan Airport EPW file. And for the quality settings, I'll also use the default low setting. And I will place a button on the canvas to run. So the objective of this first simulation is to just see the solar radiation that's incident on this roof surface for the entire year, and we'll try to focus in on the effect of overshadowing of this context building to the south. Okay, with the simulation complete, we'll utilize the outputs of the radiation map component to visualize our results back into the Rhino viewport. So to start, I will place a grid viewer component onto the canvas, and we can plug the grid output into the grid input. Now we'll get some results here on our roof, and we can fine-tune these results in order to visualize our solar radiation properly to get a sense of the overshadowing of this context building. You'll see that there is a solar radiant exposure legend here on the bottom, and there's a false color legend from 0 to 1000, and the units are kilowatt hours per meter squared. We want to increase this maximum solar radiation value so that we can see the full range of solar radiation results to get a sense of the overshadowing. Right now they're all at above 1000, so we have a kind of homogeneous yellow results grid. We can place a bounds component onto the canvas, which will give us a minimum value and a maximum value for the results. And by plugging the data output into the bounds input, we can quantify the numeric bounds of our result set. So we can see that our results range from about 1,270 kilowatt hours per meter squared all the way up to about 1,400 kilowatt hours per meter squared. So we would need to increase this, the false color maximum, to properly show the full range of results here. So to do that, we will zoom in on the grid viewer component and expose some hidden inputs. One of those is the solar radiation false color maximum. And we can incorporate this now into the component and set this to a higher number. So I'll go ahead and set it to about 1350. And I'll plug this into the solar radiation maximum input. We see that something has changed, although the results are a little bit difficult to see because of all the grid wires. So in the preview settings of our grid viewer component, I'll go ahead and turn off the grid wires option, and I'll also turn off the preview of the grid input because that is sort of clouding our results grid. And I will also, for the moment, turn off the grid layer just so we can see our results a little bit more clearly. So now you can see we have some overshadowing as a result of our context building to the south that's causing some areas of lower solar radiation falling on the roof here to the south. And we have an area of uninhibited solar radiation towards the north of our building. So that's where we'll place our PV panels. If we want to get a more detailed sense of the actual numeric values of the solar radiant exposure on our false color grid, we can zoom in onto the grid and we can turn on in the preview the sensor data here by clicking this option. And now we can see the actual numbers of each sensor in terms of the solar radiation density of each point for the given year. So now that we know where more or less we can place our PV panels, let's go ahead and run an evaluation on different orientations and sort of rotations of PV panels to see which would be the most optimal rotation to do. And I've already modeled a few examples of PV panels here on this PV layer. I'll go ahead and turn that on. You see that I have a group of 3 groups of 6 PV panels. Each PV panel is 1.5. I'll go ahead and turn off this preview for the moment. It's 1 meter wide by 1.5 meters high. The first group of 6 is on the flat, so it's basically a horizontal set of PV panels. The next group over is a group of PV panels that are rotated 21 degrees from the horizontal. I can just bring in the angular dimension tool to show that 21 degrees. And then the last group is this one right here, is rotated 42 degrees from the horizontal. And that 42 degree from the horizontal is significant because I picked that because it's approximately the latitude angle of our Boston climate. That's a kind of rule of thumb for optimizing the amount of solar radiation on a surface. So we have these 3 groups and we can evaluate the amount of solar radiation falling on a typical panel and decide which is the most optimal for our final array. To do this, I will modify the selection input here in our grid input. So instead of selecting the roof surface, I'm going to go ahead and select just the PV panels. So I'll set multiple B-reps and I will select this entire layer, all the objects on this layer. So now my grid is corresponding to these different PV panels, and I can now rerun this simulation to evaluate the solar radiation just on those panels. So I'll go ahead and call this PV panels. When it's complete, I will turn the preview on our grid viewer component, and you can see now that I have turned that on, we have our false color legend as before with our current maximum solar radiation value as 1,350 kilowatt hours per meter squared. And we see the same colored results on our PV panels. As with before, I will modify the maximum value because our results are returning some higher values. So if I scroll down on our list of bounds, we have a tree branch for each list, for each PV panel, excuse me. At the end of the list is the panels that have a higher rotation, and you can see that they have a maximum value of about 1,600. So I want to increase this maximum value to correspond. So I'll go ahead and input that higher number. So now by increasing the maximum value of solar radiation, we can see now that we have a better sense of the different solar radiation values, the total annual solar radiation on each rotation. So for 0 degrees, we have a value that is at about 1,370. And for the middle one, we have the 21 degrees, about 1,500. And then the 42 degrees, we have about 1,600. To get a better sense of which values correspond to which, we can put in a list item component and a number slider so that we can jog through the index of each grid and highlight each grid at the same time and get the results in terms of the maximum amount of solar energy density. So I will change this maximum to about, since we had 18, I'll make that 17. So we have from 0 to 17, 18 values in total. And then the list that we want to input is the grid values, and then I'll go ahead and include that here. Now I can scroll through the index here to highlight the panel of interest in our viewport, and then that will also indicate here in this panel the minimum and maximum solar energy density or solar radiant exposure kind of on that panel. So these flat panels you see that are, as I'm scrolling through these first 5 entries, these are the flat panels, and they are receiving about 1,380 or so kilowatt hours per meter squared. Now as I move to the next group, the 21 degree rotation is receiving about 1,550 or so kilowatt hours per meter squared. And then moving now to the 42 degree from horizontal rotation panels, you see that the values are a little bit higher, and they range from about 1,590 or so to 1,600. So these panels, the 42 degree panels, are the ones that are receiving the greatest amount of solar radiation over the course of the year. So I'll go ahead and reset the visualization by just plugging all of the grid outputs back into the grid input. So if we want to move forward with the 42 degree photovoltaic array, we want to see how much overshadowing, how far the overshadowing of the panels themselves cast onto the roof surface, so we can have a better idea of, if we want 2 rows of photovoltaic panels, how to space those rows. In addition to these PV panels, I want also to include the roof surface that we had originally included in our radiation map analysis. For now, I'll just actually erase the horizontal panels and the 21 degree panels so that we can only include in the scene the 42 degree rotation. So before assigning the geometry to the BREP input component, I'll want to change the name of the simulation. I'll go ahead and call this PV panels 42°. And now I can select my reference geometry for the grids. With this geometry selected, you'll see that there are 7 grids, and each grid has a certain number of sensors depending on the size of the grid. And I will go ahead and rerun that simulation. Great, now that the simulation has completed, you'll see the results reappear in our viewport, and our maximum value is still at the 1600 kilowatt hours per meter squared value that we wanted to optimize to use to visualize the tilted PV panels. But I'll go ahead and set that back to the 1350 value that we were using before to get a better sense of the overshadowing on the roof itself. So this allows us to see the effect of overshadowing of these PV panels on the roof in terms of its influence on the solar radiation on the roof for the whole year. And we can see that there is an extension of kind of overshadowing that goes back about 4 meters or so, and I could measure that using the distance tool. And from the base of the PV panel moving upward, looks like it's about 4.3 meters or so. And I can go ahead and select these panels and copy them in that way, so I can make one last test to make sure that there's no overshadowing. So we'll place them about 4.3 meters apart. And we'll do one more simulation as a test of these 2 rows of PV panels to see the solar radiation on both rows. So I'll modify this selection set and say set multiple BREPs, and I'll go ahead and select these surfaces, making sure I have the right objects selected. And I will run this one more time. So when our simulation is complete, we see now we have both rows being visualized in terms of the radiation map, and it looks like from our general first view that we are okay in terms of overshadowing. I can always increase the maximum solar radiation value on these surfaces to get a closer look. We might have a little bit of overshadowing here, and we can fine-tune this by separating and running a couple of other tests to separate them even further, or looking numerically at the values to be sure that we are optimizing our spacing. But for now, I'll go ahead and leave it at this 4.3 meter spacing. Okay, now that we've determined the right place on the roof to place our PV system, and we've optimized the spacing and rotation angle of our panels, we can switch now over to ArcSim in order to simulate the electricity produced by our PV system using Energy Plus as our simulation engine. So we can do this by placing the PV component onto the canvas. It's located here. And our first input is the panel's input. Now we actually need another component in order to properly input Rhino geometry into the simulation. So we'll place this PV panel component first, and then a BREP component. We'll use the BREP component to reference our PV geometry. And we'll input that PV geometry into the surface input. Now this PV panel component will convert these surfaces into a format that is legible for Energy Plus. And one of the things that we need to define the performance of these panels is to indicate the efficiency of our PV system. So the default value for the PV efficiency is 15% and is expressed as a fraction, so it's 0.15. That basically means 15% of the solar energy will be converted into electricity. We'll leave that as the default for now. And the area, in terms of what part of our surface is actually is the effective area for converting solar energy into electricity, the default there is 0.8, but I'll just go ahead and set that to 1. So that means that the panel that we're using, so we have a 1 meter wide by 1.5 meter high PV panel. That entire surface area is used for converting solar energy into electricity. Now we can plug this panel output into the panel input of the PV component. Next, it's asking for contextual shading. Now, while we've taken steps to ensure that the neighboring tower, isn't overshadowing onto our PV panels, but it's probably a good idea to include our context geometry. So I'll go ahead and put another BREP container onto the canvas and set one BREP for our neighboring building. I'll plug that into the simulation. Turn the preview off. Next, we need to give our simulation a name. So I'll call this PV. The next input is the directory. So this is where we can tell ArcSim where to save all of the input and results files for the simulation. And you see that the default is the desktop. So I'll go ahead and leave the defaults for now. Next, we have the EPW file. As with the DIVA simulation components, we need to provide a climate, and so we'll want to be consistent and use the same climate file, and we'll go ahead and keep the Boston Logan Airport EPW file for that. And to run the simulation, we can place a button on the canvas. Although before I run the simulation, we should take a look at the settings. So this is just going to this is the place where we can define the run period. So we want to make sure that we keep this as an annual simulation, as we did with the radiation maps. We want to know how much electricity is produced over the whole course of the year. Although we can change this to see how much electricity is produced in the summer or in the winter and things like that. For now, we'll leave it as the defaults, and we'll leave the resolution as monthly so we can see the electricity output for each month of the year. And if we scroll down here on the output variables, while we can't change this gives us a sense of what the results will be. You see that it's checked by default, generator produced DC electric energy. So that's the result metric that we're going to be getting, and that's going to be expressed in joules. And we'll be getting an output for each PV panel that we input. Okay, so I'll go ahead and run the simulation after we've made these settings. Now the results won't be previewed in the Rhino viewport. Rather, we get a CSV output path, and then we have a model output. So the results are actually a set of data that we can visualize back into the Rhino viewport through other components. We can open them up directly in a program like Excel, or we can display the numbers here in the Grasshopper canvas just to get a sense of our solar energy output. So I'll go ahead and do that. And first we need to place this load results file component onto the canvas in order to parse out the results. So to begin, we need to plug the model output into the model input of this component. We have the option to normalize the results. So if we want to normalize the results over the surface area of each panel, and I'll just leave it as false for now. And the toggle, we need to toggle this as true in order to generate the results. So I'll place a Boolean toggle on the canvas and set that to true. You'll see that now we have a preview of our panels here on the Rhino viewport. I'll go ahead and turn the preview off in our Diva grid so we can see this a little more clearly. So these are being previewed. This indicates that these surfaces were in fact input and modeled using Energy Plus as the simulation engine. And I can now look at the results in the form of a panel. So here we have the results. We have a tree that has a branch for each panel, and within each branch is a list of the DC electric energy produced in joules for every month. Now we can just add up all this data by placing a mass addition component onto the canvas. If we were to input this and flatten the results, we can get a total joules value for the entire array. So this tells us what the DC energy, the DC electricity output is for the entire array. And if I want to express this in kilowatt hours, I can put a division component onto the canvas and divide the joules number by the conversion factor from joules to kilowatt hours, which is 3,600,000. And I can now express this entire output in terms of kilowatt hour. So our total DC electricity energy output is 4,322 kilowatt hours total. And to keep in mind, this is only the ideal sort of DC electricity output for the PV panel array. So it's not doesn't take into account conversion losses for AC energy or other types of performance losses like residue and other factors. We can further manipulate this data by flipping this tree in order to get a kind of monthly graph. So if I were to just place a flip matrix component here, now we have a branch for each panel and then a list of the 12 months. But if I were to flip these results, I now have a branch for each month and a list for each panel. So I can add these up using the mass addition component and flattening that to make it into one list. So now you can see that I have a total value for the whole array for each month. So I can take this monthly data into Excel to show this as a monthly graph, or I can, just to get a quick sense of what the monthly curve looks like, I can plug these results into a quick graph component just to see what the values are in terms of the monthly results. And if I want to show it in kilowatt hours, I can plug in, I just copied and pasted this division component, and I could plug those results in. And here we can see the results for the months of the year in kilowatt hours. All right, that about wraps up this tutorial. We looked at how to evaluate the overshadowing of a rooftop using a radiation map within the Grasshopper canvas, finding the right place for a PV system, optimizing the PV system's rotation and spacing using that radiation map component in Diva, and then taking advantage of the ArcSim PV panel component to figure out what the annual DC electricity output is for that system. Thanks a lot, and I hope you join us for the next tutorial.